cans, two 16-ounce cans, basically a little bit of ethanol and water and nitrogen for $10.98. And then maybe the cost is because you need an appropriate nozzle so that the drops of spray vaporize immediately upon spraying into the hot car. So how would you calculate work, heat, delta E, delta H, delta S, and delta G for this process? Okay, so let's actually do this first. Okay, so let's just draw a little picture. Here's your car. Here's your car, and it's really hot. Make sure you don't have your dog in the car when it's 130 degrees, because that's not going to be good for your dog. Okay, so here's your car. So it's 130 degrees in here. You spray the instant car cooler in here. So what's going to happen to the spray? It's going to evaporate. So you have your H2O. Liquid is going to be converted into H2O gas. Okay, so how we can do this, we can say that we have H2O liquid at a temperature of something, that's converted to H2O gas at a temperature of something. So what temperature is this water being converted into a gas according to this problem statement? Yeah, so it's actually being converted to a gas not at 100 degrees Celsius but at 55 degrees Celsius. And what is going to be the temperature of this gas? Now, when a liquid boils, as it's boiling, what happens to the temperature of that liquid? Does it stay the same? Does it increase or decrease? Yeah, so that means the temperature here, if it's staying the same, should be 55 degrees. So really what you're doing is we're also doing this, rather than, just to make it easier, we're going to assume that the instant car cooler is 100% water rather than 10% alcohol and 90% water. So just to make it a little easier. Okay, so what we want to do is we want to figure out Q and W and delta E and delta H and delta S and delta G for this process. Now, when you look at appendix 2 in the textbook, is the temperature for delta H a formation of liquid water and steam at 55 degrees. What is the temperature of delta H in appendix 2? It's at 25 degrees. So to calculate these quantities here, here's one way you can do it. This is the path you can take. You can go from H2O liquid at 55 degrees to H2O liquid at 25 degrees, because we can look this up in appendix 2. And then we can go from H2O liquid to H2O gas. And again, this is at 25 degrees from appendix 2. Okay? And then once we have this, we can go from H2O gas back to H2O. So H2O gas at 25 to H2O gas at 55. Okay, so note that we have three steps in the path that we're taking. So how would you, now again, we can directly measure Q and W, and then we can relate Q and W to delta E, delta H, delta S, and delta G. Okay, so before we start, what is the formula for Q? So we can calculate Q. So Q, no, so we don't know what delta H is yet. So we can directly measure Q using what formula? Yeah, so we can use M times S times delta T. Okay, so again, we can directly measure Q using this formula. We can directly measure work using what formula? So work is equal to, minus P times delta V. Okay, so using these two formulas, we can directly calculate Q and W. Now that we know Q and W, we can calculate delta E. So again, we cannot directly measure delta E, but we can relate this to Q and W. So how is delta E related to Q and W? So this is equal to Q plus W. And then we can calculate delta H. So how is delta H related to Q or W or both?
It's equal to Q.
Yes, that's equal to Q. And then for delta S, how is delta S related to Q or W?
Q over T.
It's Q over T. Now it's actually greater than or equal to Q over T. Okay, so if the system is at equilibrium, delta S equals Q over T. If it's not at equilibrium, then it's greater than Q over T. And then finally for delta G, how do we calculate delta G? That's equal to delta H minus T delta S. So if we go back to step 1 here, can we measure Q for this step, going from H2O liquid at 55 degrees to H2O liquid at 25 degrees? Yes, we can do that. So note that for this step here, Q1, okay, so Q for step 1 is equal to M times S times delta T. So let's see, let's just say we have 1 gram. We have 1 gram of water. We know that M is equal to 1 gram. We know what the specific heat of water is. What would delta T be? So delta T is T final minus T initial, so that's going to equal, so that'd be 25 minus 55. Okay, so there's our Q1. What can we say for W1, the work for step 1? So we know that work refers to gases only. Are there any gases involved from the liquid going to the liquid at different temperatures? No. So that means that work for step 1 equals 0. For step 2, can we figure out Q?
S is log?
Yep, S is log. So what we would do is we say for Q2, that's going to equal the delta H vaporization, and we can look up delta H of formation at 25 degrees for H2O liquid, delta H formation of H2O gas at 25 degrees, that tells us delta H of vaporization. And then for work, we'll call it W2, is work going to be equal to 0 for step 2. Because note that we have a gas product and a liquid reactant. So that means that delta N is going to be positive, which means that work is going to be negative. So we can actually, work is going to be less than 0. So how would we calculate work here then? What formula will we use? We can use P delta V. Okay, so if for W2, that's equal to minus P times delta V, or we can say it was equal to minus delta N times RT. Okay, so we know what the temperature is, 25 degrees or 298 Kelvin. For R, we can look up the gas constant. What would we use for delta N? Yeah, so we have, if we have 1 gram of, water converted to 1 gram of steam, we want to calculate for delta N, not just 1 mole, but okay, so the moles of gas is going to equal okay, so we have 1 gram of steam. So we have 1 gram divided by the molar mass, 18 grams per mole system. So this will give you the moles of gas. Okay, so once we know the moles of gas, there's no moles of gas on the reactant side, so delta N is equal to this number here. Then we can multiply by R times T, and that gives us work. For the third step, how do we calculate Q3?
MS delta T.
So what formula will we use?
MS delta T.
Yeah, MS delta T. Now, we'd have to look up the specific heat of steam, which is different than the specific heat of water in the liquid state. Okay, so that's a little bit different, but yeah, do the same thing. We have M, look up the specific heat of steam. What's delta T going to be? Yes, this is going to be 1 gram times the specific heat of steam times 55 minus 25. And then for work, for step 3, that's going to equal okay, so we have, let's see, we have 1 gram of steam at 25 going to 1 gram of steam at 55. So work is going to equal is 0. How can work equal 0? Because delta N equals 0. Okay, so you calculate Q1, Q2, and Q3, so Q total is equal to Q1 plus Q2 plus Q3. And then for work, the total work is going to equal W1 plus W2 plus W3. So now that you know Q total and W total, can you calculate delta E? Yeah. So delta E, like we said over there, is equal to Q plus W. Delta H is equal to Q total. Delta S is equal, or actually greater than or equal to Q divided by T, and then delta G is equal to delta H minus T delta S. Okay, so would you expect delta G to be greater than 0 or less than 0? Okay, so if you spray this instant car cooler into a hot car, and the car is cooled, the air inside the car is cooled from 130 degrees Fahrenheit to 77 degrees Fahrenheit, is that a spontaneous reaction? Yeah, so that means delta G should be less than 0. Now note that the liquid is being converted to a gas, so is delta H, should that be greater than 0 or less than 0? If the liquid is converted to a gas. Okay, so delta G should be less than 0. Delta H should be greater than 0. For delta S, we expect that to be greater than 0 or less than 0. Should be greater than 0.
Yeah.
Now there's two reasons. Note that we have a liquid going to a gas. Which state of matter is more disordered or more random? Yeah, gas. And then if you look at this formula here, remember that there's two driving forces which determines whether a reaction occurs. So we want delta G to be less than 0. And if delta H is greater than 0, that means delta S has to be greater than 0. Okay, then for delta E, then we'll do our calculation. Delta G. So I mean for delta, so would you expect delta E to be greater than 0 or less than 0? Less?
Yeah. That's kind of cool.
Here's less. Yeah, because in terms of temperature, the temperature is the same. Okay, we're just saying that the temperature is still 55, because really from here, then the temperature is going to go down to T